There is a signal, faint, ancient, and impossibly old. It whispers from the void. It is a cosmic fossil, etched into the fabric of space itself, a remnant from a time that, by every law of physics, should not exist, a time before time, a moment before the moment of creation. For decades, the story of our universe began with a singularity, a point of infinite density, the violent birth of space and time in the Big Bang. Nothing came before, because before had no meaning. But what if that story is incomplete? What if the universe has a memory? This is the haunting possibility raised by an anomaly buried in the oldest light we can see. A subtle pattern that suggests an echo from a previous cosmos. It is a clue that the universe might be cyclical, eternal, and that our entire cosmic history is but one chapter in an infinite book. This is the search for the signal from before the Big Bang. Chapter 1. Discovery Phase. The universe, for centuries, was a magnificent clockwork. A grand, predictable mechanism where time was a constant, unwavering river flowing from past to future, and space was a static, immutable stage upon which the drama of planets and stars played out. This was the world Isaac Newton bequeathed to science, orderly, absolute, and knowable. But in the quiet of a patent office in Bern, Switzerland, a young clerk was dreaming of a different cosmos, and in 1905, with a series of papers that would shatter the foundations of physics, Albert Einstein began to dismantle the clockwork. He proposed a radical, almost heretical idea that the speed of light is the only true constant in the universe. Everything else, space, time, even reality itself, is fluid, malleable. Time does not tick at the same rate for everyone. A clock in motion runs slower than a clock at rest. A ruler measured while moving is shorter than one measured at rest. This was not a quirk of perception. It was a fundamental property of the universe. Special relativity revealed a cosmos where space and time were not separate entities, but woven together into a single, four-dimensional fabric, space-time. It was a breathtaking revelation, but for Einstein, it was only the beginning. He saw a flaw. His 1905 theory described a universe without gravity, and so, for 10 years, he wrestled with a single, monumental question: how to make gravity fit into this new, relativistic world. The answer arrived not as a force, but as a geometry. In 1915, his theory of general relativity was born. He proposed that mass and energy do not exert gravity, they shape space-time. A star, a planet, a galaxy, they depress the fabric of the cosmos, creating a curvature. What we perceive as gravity is simply matter following the contours of this warped geometry. Earth orbits the Sun not because of an invisible string of force, but because it is rolling along a groove in space-time carved by the Sun's immense mass. It was a concept of profound beauty and almost poetic elegance. The universe was not a clockwork stage, but a dynamic, elastic membrane, breathing and bending under the weight of its own contents. But a theory, no matter how beautiful, must face the cold, hard light of evidence. The first great test came in 1919. Sir Arthur Eddington led an expedition to the island of Principe off the coast of Africa to observe a total solar eclipse. According to Einstein's calculations, the Sun's mass should bend the space-time around it, deflecting the light from distant stars that passed near its limb. As the moon slid before the Sun, plunging the day into an eerie twilight, Eddington's telescopes captured the displaced starlight. The measurements matched Einstein's predictions precisely. The fabric of space-time was real. It could be bent, and if it could be bent, then it could be made to ripple. For decades, this remained a theoretical curiosity. Then, in 1967, a new and utterly perplexing signal was detected. A graduate student at Cambridge, Jocelyn Bell Burnell, was reviewing data from a radio telescope she had helped build when she found it. A pulse. Incredibly rapid, impossibly regular. It beat with a rhythm more precise than any atomic clock. For a brief, thrilling moment, the possibility of an artificial source, a signal from an extraterrestrial intelligence, was entertained. They were jokingly labeled LGM1 for little green men. But the truth was, in its own way, Even more astonishing, they had discovered a pulsar, a rapidly spinning neutron star, the collapsed, ultra-dense core of a dead sun, sweeping beams of radiation across the cosmos like a lighthouse. These cosmic metronomes, these natural clocks of staggering precision, would become the universe's greatest gift to cosmologists. They were the perfect instruments for probing the subtle textures of space-time itself, because if space-time is a fabric, then any movement within it should send out tremors. A pulsar, especially one in a binary system with another dense star, provides the perfect laboratory. As two such massive objects orbit one another at tremendous speeds, they are predicted to lose energy in the form of ripples in space-time, gravitational waves. In 1974, astronomers Joseph Taylor and Russell Hulse discovered just such a binary pulsar. Over years of observation, they found its orbit was decaying at exactly the rate predicted by general relativity. The energy was being carried away by these invisible waves. It was an indirect but stunning confirmation. The universe was not silent. It was ringing like a bell. And if gravity could slow time and warp space, its effects could be measured here, on Earth. Atomic clocks, capable of measuring time with nanosecond precision, provided the proof. A clock placed at a higher altitude, farther from Earth's mass, and thus in a slightly weaker gravitational field, ticks faster than an identical clock at sea level. The difference is infinitesimal, but it is there. Time itself flows at different rates on a mountaintop than in a valley. We do not perceive it, but our technology does. The very GPS that guides our cars must account for this relativistic time dilation. Without these corrections, the system would drift into uselessness within minutes. Einstein's equations are not abstract mathematics. They are encoded into the operation of our daily world. These were the first whispers, the initial clues that the cosmos was far stranger and more fluid than anyone had imagined. Einstein's insight had unlocked a new way of seeing. It revealed a universe where time was a river that could speed up or slow down, where space could stretch and compress, and where massive objects in motion could send ripples across the cosmic medium. They had discovered the grammar of the cosmos. They could now listen, and soon they would hear something that should have been impossible, an echo from a time before time began. Chapter 2: Scientific Shock. The confirmation of Einstein's universe was a triumph of human reason. A century of discovery had mapped the contours of reality, revealing a cosmos governed by the elegant geometry of space-time. The laws of physics were the rules of this geometry, and they painted a clear, if complex, picture of cosmic history. It was a story that began with a singularity, a point of infinite density and temperature, where the laws of physics themselves broke down and ceased to function. From this unknowable origin, the universe exploded into being in the event known as the Big Bang, expanding and cooling for over 13 billion years to become the tapestry of galaxies we observe today. This was the established canon of cosmology. It was a complete, self-contained story, and the discovery of the cosmic microwave background radiation, the faint, thermal echo of that primordial fireball, was the definitive proof, the final piece of evidence that sealed the narrative. The universe had a beginning, and before that beginning, there was nothing. No space, no time, no physics, no before. This is why the proposal, when it came, was not merely contested, it was heresy. It emerged from a deep and meticulous study of the universe's oldest light. The WMAP and later Planck satellites had not just found the CMB, they had mapped it in exquisitely precise detail, creating a full sky image of the infant universe, a fossilized snapshot of its first moments of structure. Within this map, scientists expected to find a random, Gaussian distribution of hot and cold spots, the quantum seeds, stretched by inflation, that would eventually grow into galaxies and clusters. This randomness is a core prediction of the inflationary model. It is the signature of a universe born from a single, isolated quantum fluctuation. But a team of researchers, including the renowned physicist Roger Penrose and his colleague Vahe Ghosadian, claimed to have found something imprinted upon this randomness. A pattern, a series of faint, concentric circles within the CMB map, regions where the temperature variations were anomalously low. These were not the random imperfections of birth. They were coherent structures, and their proposed explanation was a thunderclap in the quiet halls of theoretical physics. These circles, they argued, were the imprints of gravitational waves generated by the most violent events imaginable in the previous cosmos. The collisions of supermassive black holes. They were cosmic bruises, echoes of a time before the Big Bang. The scientific shock was immediate and profound. The proposal violated the most fundamental premise of modern cosmology. The Big Bang was the absolute beginning. The concept of a before is not just unproven. Within the standard model, it is meaningless. Time itself was created in that event. To speak of a prior existence is akin to asking what is north of the North Pole. The singularity is the ultimate barrier, a veil beyond which no information, no energy, no signal of any kind could possibly pass. It is the hard edge of reality. Penrose's Conformal Cyclic Cosmology, CCC, suggested this veil was an illusion. It proposed that our universe is but one in an endless cycle of aeons, each beginning with its own Big Bang and ending in an exponentially expanding void of nothingness. At the end of time, when the universe contains only massless photons and space-time is stretched into a featureless, smooth state, it becomes mathematically identical to the high-energy, dense state of a new Big Bang. The infinite future of one aeon seamlessly becomes the singularity of the next. In this model, the circles are Hawking points, the ghostly signatures of the final, evaporating black holes from the previous aeon, their radiation somehow imprinted onto the new one. The backlash was not merely academic, it was almost instinctual, a defense of a deeply ingrained paradigm. Critics pounced. The analysis, they argued, was flawed. The circles could be statistical illusions, artifacts of the specific way the data was processed, or simply the result of chance alignments within an inherently random field. They argued that the methods used to find the circles were susceptible to confirmation bias, that if one looked hard enough for patterns in the cosmic static, one would inevitably find them. The Planck collaboration itself performed its own, more comprehensive analysis and stated it could find no statistically significant evidence for the concentric circles, declaring the anomalies consistent with the standard model of cosmology. The signal, if it existed, was buried in noise. It was a phantom, a cosmic mirage. Yet, the idea persisted. It held a terrifying, mesmerizing allure. Because if it were true, it meant that our entire understanding of the universe's origin was a provincial mistake. We had been studying a single chapter and believing it was the entire book. The shock was not just about a potential discovery. It was about the nature of science itself. It forced a confrontation with the limits of our knowledge. The Big Bang singularity had always been the ultimate refuge of ignorance, the point where science could comfortably say, "We do not know, and perhaps cannot know." It was a line drawn in the sand. The suggestion of a pre-Big Bang signal was not just stepping over that line, it was erasing it entirely, forcing science to gaze into an abyss of infinite regression. It raised a terrifying and thrilling possibility, that the universe is not only stranger than we imagine, but that it may have a memory, and that we might, just might, be able to read it. Chapter 3. Deeper Investigation. The initial shock of the proposition gave way to a more sober, more determined phase, the deep investigation. A claim of this magnitude could not be dismissed with a single refutation, nor could it be accepted on the strength of a single analysis. It demanded a forensic-level scrutiny of the cosmos. The debate moved from the philosophical to the intensely technical, a painstaking archaeological dig into the faintest light in the universe. The Planck satellite had provided the most detailed map of the cosmic microwave background ever created, a high-resolution photograph of the universe's infancy. This map became the primary crime scene, and every physicist a detective searching for fingerprints of a previous existence. The investigation bifurcated. One path focused on the statistical forensics of the CMB itself. Teams around the world developed new, more robust algorithms to search for non-random patterns, specifically the concentric circles Roger Penrose had proposed. They were not just looking for circles, they were hunting for any form of non-Gaussianity, a statistical term for a deviation from perfect randomness. In the standard inflationary model, the fluctuations in the early universe should be almost perfectly Gaussian, a symphony of quantum noise with no repeating melodies or coherent rhythms. A signal from a prior eon would be a distinct melody woven into that noise, a pattern that breaks the harmonic rules. Some independent analyses claim to find supporting evidence, subtle concentric anomalies that were hard to explain by chance alone. Others found that such features could indeed arise in simulated, purely inflationary universes. The statistical evidence remained infuriatingly ambiguous, a Rorschach test in the cosmos where experts saw either profound structure or mundane noise. The second path of investigation sought to find alternative, corroborating evidence. If concentric circles were too subtle, perhaps other anomalies would point in the same direction, and the universe provided a colossal one, the cold spot. This is a vast, perplexingly cold region in the CMB, an area of space far larger than standard inflation should allow. It is a cosmic void of unexplained origin. Some theories proposed it was the imprint of a colossal supervoid, a vast emptiness in the distribution of galaxies. But observations could not find a void large enough to explain it. This left room for more exotic explanations. Perhaps the cold spot was a scar, a collision. In the multiverse theory, our universe is one bubble in a frothing meta-universe of inflating bubbles. The cold spot, some proposed, could be the bruise left by our nascent universe grazing against a neighbouring bubble universe in the multiverse foam. This was a different kind of pre-Big Bang cosmology, but it pointed to the same profound idea, that our universe is not alone, and its birth was not an isolated event. The plot thickened further with the pursuit of the universe's very first tremors, primordial gravitational waves. These are ripples in the fabric of space-time, predicted to have been generated during the violent period of inflation, a fraction of a second after the Big Bang. Their detection would be the ultimate smoking gun for the standard inflationary model. In 2014, the BICEP2 collaboration announced they had found them a pattern of B-mode polarization in the CMB, thought to be caused by these ancient waves. The scientific world held its breath. It appeared to be the final, triumphant validation of the standard model, but the breath soon turned to a sigh. The signal was found to be contamination, mere cosmic dust within our own galaxy, mimicking the hoped-for pattern. The absence of a clear, strong signal for primordial waves was, in its own way, another anomaly. It left the door open, for conformal cyclic cosmology predicts a different kind of gravitational wave background, not a smooth, random hum from inflation, but sharper, more distinct signals from the cataclysmic events of a previous aeon. This period of deeper investigation did not provide answers. It multiplied the questions. It revealed that the initial mystery of the circles was merely the first thread, and pulling on it began to unravel the entire sweater of cosmic origin. The anomalies were no longer isolated curiosities. They were interconnected clues. The circles, the cold spot, the silent echo of gravitational waves. They were pieces of a puzzle so vast no one yet knew what the picture was supposed to be. The investigation had transcended a single theory. It was no longer just about proving or disproving Penrose's model. It was a fundamental interrogation of the Big Bang paradigm itself. The universe, through its most ancient light, was whispering a secret it had held for 13.8 billion years. And the hardest thing to accept was that the secret might be that our beginning was not the beginning at all, but a transition, a rebirth, a moment in an infinite cycle where the universe, in its final act of forgetfulness, lets slip a memory of its past life. Chapter 4. Escalation. Mystery deepens. The initial, singular anomaly, the faint suggestion of circles in the cosmic static, was no longer the core of the mystery. It had been the first crack in the dam. Now, the investigation revealed the entire structure was under strain. The deeper physicists looked, the more the cosmos seemed to defy a simple, singular origin story. The mystery was no longer just about a signal. It was about the foundational stability of the universe itself. The questions escalated from what existed before to whether the very laws of nature are constant or merely temporary tenets in a cosmic cycle. The most profound escalation came from a discovery that seemed entirely separate, yet felt deeply connected: the phenomenon of dark energy. In the late 1992, astronomers made the shocking discovery that the expansion of the universe is not slowing down, as everyone had assumed. It is accelerating. Some unknown repulsive force, counteracting gravity, is pushing galaxies apart at an ever-increasing rate. This force, dubbed dark energy, now constitutes the majority of the universe's energy budget. For the standard model, this was a perplexing addition. For cyclic models, it was the key to the entire cycle. In Conformal Cyclic Cosmology, the accelerated expansion is not a puzzle. It is the engine of renewal. It is the necessary process that, over trillions of years, will expand the universe into a featureless, empty void. It will dilute matter and radiation until only photons remain, stretching space-time until it loses all sense of scale and curvature. This bleak, eternal end state is the very same mathematical condition as the low entropy, smooth beginning of a new Big Bang. The accelerating expansion, the great mystery of modern cosmology, becomes the mechanism that erases the universe and resets it, ready for a new aeon. The force that seemingly dooms our cosmos to a lonely fate is the very same force that enables its rebirth. This revelation tied the distant future directly to the remote past, creating a terrifying and beautiful symmetry. It suggested that the constants of nature, the finely tuned numbers that allow atoms and stars and life to exist, might not be fundamental. Perhaps they are reset with each new aeon. The mystery then deepened from what came before to why is our universe so habitable? The answer could be an eternal Darwinism on a cosmic scale. If universes are born and reborn in an infinite cycle, then the physical parameters are not fixed. They may change with each iteration. We exist in this particular aeon with these specific constants, not because of a singular, miraculous fine-tuning, but because this is a stable configuration that has emerged from an infinite series of trials. Our universe is hospitable because only in a hospitable universe could someone ask the question. This concept, the cosmological application of the anthropic principle, moved the mystery from the realm of astrophysics into the domain of philosophy. Furthermore, the search for evidence began to point to even grander, more unsettling possibilities. The investigation into the CMB's anomalies suggested that if a pre-Big Bang structure existed, it wouldn't just be a uniform, prior universe. It would have its own history, its own topography. The concentric circles, if real, were evidence of specific, catastrophic events. The cold spot could be evidence of a large-scale collision or flaw in the space-time of the previous aeon. This meant that the initial conditions of our universe were not perfectly smooth and homogeneous, as inflation demands. They were imprinted with the scars of a previous existence. This directly challenges the need for a period of inflation itself, the cornerstone of modern Big Bang cosmology. Inflation was invented to solve the problems of the standard model, to explain why the universe is so flat and uniform. But if that uniformity is an inheritance, a legacy from a prior aeon that met a similar end, then inflation becomes an unnecessary epicycle. The mystery thus escalated to a potential paradigm shift, threatening to unseat the theory that has dominated cosmology for 40 years. The escalation was no longer about a single data point. It was a convergence of crises. The acceleration of the expansion, the potential anomalies in the CMB, the philosophical problem of fine-tuning each on its own was a major puzzle. Together, they pointed to a cosmos far more vast, ancient, and mysterious than the standard model allowed. The universe was not content to be known. It presented a picture of an eternal return, a cosmic Ouroboros eating its own tail, where the end is written into the beginning, and the greatest mysteries of our future are the only keys to understanding our deepest past. The search for a signal from before the Big Bang had become a referendum on the nature of time, eternity, and the very laws of physics themselves. Chapter 5. Theories and Speculations. The mounting anomalies could no longer be dismissed as mere cosmic static. They were persistent, coherent whispers from the edge of time, demanding an explanation, the investigation had pushed cosmology to a precipice. To step forward, science had to venture beyond the comfortable confines of the standard model and into the realm of profound speculation, where mathematics and metaphysics intertwine. The quest to explain the signal from before the Big Bang fractured into multiple, competing visions of reality, each a grand narrative attempting to weave the disparate clues into a coherent tapestry of cosmic genesis. The first and most conservative theory remains the standard inflationary model, albeit with modifications. Its proponents argue that the anomalies are not signals from a prior universe, but are instead artifacts of a more complex inflationary phase within our own. Perhaps inflation was not a single smooth event, but occurred in fits and starts, in a series of bubbles, of space-time nucleating and expanding. A collision between two such bubbles in our own early universe could potentially create features like the cold spot or unusual polarization patterns. The concentric circles could be explained by rare, but not impossible, statistical fluctuations within the quantum fields that drove inflation. In this view, the standard model is not broken. It is merely more intricate than previously imagined. The universe is still a one-time event, a singular genesis from nothingness. The burden of proof, they maintain, remains on those who would shatter this paradigm. In stark opposition stands Conformal Cyclic Cosmology, CCC, the theory that gave birth to the entire inquiry. Developed by Roger Penrose, CCC is a radical vision of an eternal, cyclical universe. It proposes that the universe progresses through endless cycles, or aeons. Each aeon begins with a big bang and expands outward, dominated first by radiation, then matter, and finally by the dark energy that accelerates its expansion to a state of ultimate thinness and uniformity. In this distant future, all matter has decayed or been sucked into black holes, which themselves evaporate via Hawking radiation. The universe is left as a vast, empty sea of massless photons. Crucially, in this state, the concept of scale becomes meaningless. A universe devoid of mass and stretched to infinity is mathematically identical to a universe of infinite density at a point. This conformal rescaling allows the infinite future of one aeon to become the Big Bang singularity of the next. Information is not lost, it is transformed. The gravitational shockwaves from the most colossal events of the previous aeon, the collisions of supermassive black holes, imprint themselves as faint, concentric circles of temperature variation, Hawking points, in the CMB of the next. CCC is not just a theory of a prior universe, it is a theory of cosmic reincarnation. A third path is offered by the ekpyrotic and cyclic models, born from string theory. This vision suggests our universe is a three-dimensional brane, short for membrane, existing in a higher dimensional bulk. Other branes may float in this bulk. In this scenario, our Big Bang was not a birth from nothing, but a rebirth from collision. It was the moment when our brain collided with another parallel brain universe. The tremendous energy of this impact ignited the hot, dense state we call the Big Bang and set our universe expanding. This model is inherently cyclic. The branes, attracted by gravitational force, could oscillate, colliding and separating over vast trillions of year timescales, creating a new universe with each collision. A signal from before could be an imprint from the other brain, or a relic of the space-time of our own brain from the long, cold contraction phase that preceded the collision. Here, the pre-Big Bang era is not another aeon, but another dimension. Finally, there is the quantum cosmology perspective, which seeks to apply the rules of quantum mechanics to the universe as a whole. One interpretation suggests that the universe, like an electron, can exist in a superposition of states until it is observed. The Big Bang singularity, in this view, is not a barrier, but a quantum transition. Theories like quantum loop gravity attempt to model this, replacing the singularity with a quantum bounce, where a previous contracting universe reached a maximum density and then rebounded into our expanding one. The signal, then, would be quantum information that tunneled through the bounce. Another, even more speculative idea is the cosmic inflation as a quantum fluctuation hypothesis, which posits our entire universe is a rare but statistically inevitable fluctuation in a primordial, eternal quantum field a bubble of order in a sea of chaos. Each theory is a magnificent castle built on a foundation of mathematics and imagination. Each explains some anomalies while struggling with others. None can yet claim victory. They represent not a failure of science, but its ultimate ambition. They are competing answers to the most profound question we can ask, and the search for the signal is the jury, listening for a verdict from the dawn of time. Chapter 6: Scientific Tools and Ongoing Testing. The grand theories of cosmic origin are monuments of human intellect, but they are built on sand until tested against the cold, hard light of reality. The debate over a signal from before the Big Bang has therefore moved from the chalkboard to the laboratory, launching a global, technological race to build the instruments sensitive enough to listen to the faintest whispers of creation. This is no longer a philosophical exercise. It is an empirical siege on the boundaries of time, employing telescopes that are time machines, detectors that feel the tremors of space-time itself, and colliders that recreate the conditions of the first moments. The hunt for the signal is now a story of engineering and patience. The primary tool remains the cosmic microwave background, but we have moved far beyond simply mapping its temperature. The new frontier is polarization. The light of the CMB is polarized in specific patterns, a direct result of its interaction with the fabric of the universe in its first instance. The faint B-mode polarization pattern, the curl-like signature, is the ultimate prize. It is a double-edged sword. It can be created by the primordial gravitational waves of inflation, but also by the gravitational lensing of the CMB light as it passes through the large-scale structure of the universe over billions of years. Disentangling these two signals is the monumental task of a new generation of observatories. Projects like the Simons Observatory in Chile's Atacama Desert and the upcoming Lightbird satellite mission from Japan are being meticulously designed with this sole purpose. Their ultra-sensitive arrays of detectors will scan the microwave sky with unprecedented precision, searching for the specific statistical imprints that could distinguish a standard inflationary pattern from something far stranger, like the sharper, more localized zingers of gravitational waves from pre-Big Bang black hole mergers predicted by CCC. To directly detect those gravitational waves, a new era of astronomy is dawning. The Laser Interferometer Space Antenna, LISA, a joint ESA-NASA mission slated for the 2032, will be the first dedicated space-based gravitational wave observatory. While LIGO and Virgo on Earth listen for the high-frequency chirps of stellar mass black holes, LISA will operate in a gravitational wave sweet spot, sensitive to the low-frequency hum of the cosmos. It will hear the mergers of supermassive black holes, the very events proposed to create the concentric circles in the CMB. If Penrose's theory is correct, LISA should not only detect these mergers, but it should also find evidence of their remnants, a stochastic background of gravitational waves with a specific frequency signature that differs from the smooth hum predicted by inflation. It would be the sound of the previous aeon, a chorus of echoes from a dead universe. On the ground, particle physicists approach the problem from the other end of time. The Large Hadron Collider and future colliders, like the proposed Future Circular Collider, do not look out into space. They look inward, recreating the conditions of the universe mere fractions of a second after the Big Bang. By smashing particles together at energies that approach those of the primordial fireball, they probe the fundamental symmetries of nature. They are testing the stability of the Higgs field, the field that gives particles mass, and hunting for any sign of new physics, such as supersymmetry or extra dimensions, that could provide a mechanism for a cyclic universe or a quantum bounce. They are searching for relics, hypothetical particles like magnetic monopoles or gravitinos that could have been created in a previous cosmos and survived the transition. Their quest is to find any crack in the standard model of particle physics that would force us to rewrite the story of the beginning. And silently, in the darkness of space, other missions gather clues. The James Webb Space Telescope, with its unparalleled infrared vision, peers back to the very first galaxies. By understanding the precise conditions of the early universe, it provides critical data that constrains the models of inflation and structure formation. Any deviation from the expected pattern of galaxy evolution could be another hint of anomalous initial conditions, a fingerprint of a prior existence. This global effort is a testament to a single, driving human need: to know our origins. It is a painstaking process of elimination, of testing each magnificent theory against the unyielding data of reality. The tools are not just machines, they are extensions of human curiosity, designed to listen for a story told in the language of gravity, light, and quantum fields. They are all tuned to the same frequency, waiting for the universe to break its silence and speak, finally, of what came before. Chapter 7. Philosophical Reflection. Emotional Close. The search ends not with an answer, but with a deeper, more resonant silence. The concentric circles may yet be statistical phantoms, the cold spot a cosmic coincidence. The gravitational waves from the dawn of time remain elusive, their message still encoded in the quiet. But the true impact of this quest was never contingent on a definitive discovery. It was in the asking of the question itself. For in reaching for a signal from before the Big Bang, humanity did not simply push the boundaries of science. It staged a profound rebellion against the very idea of a boundary. We attempted to look beyond the ultimate horizon, to seek a memory in a place where memory should be impossible. This endeavor forces a reckoning with the nature of time. We have long conceived of it as a linear river, flowing from a definitive source in the past toward an unknown sea in the future. But the cyclic models, the quantum bounces, the colliding brains, they suggest a different geometry. Time may be a circle, a spiral, or a vast, branching tree. The arrow of time, the relentless increase of entropy that gives us a sense of past and future, may not be a fundamental law but a local condition, reset with each new aeon. Our lived experience of cause and effect, of history and destiny, could be a provincial perspective, true only for this chapter of a much grander story. We are like characters in a single volume who have suddenly become aware of the infinite library that may contain us. This changes the meaning of our existence. If the universe is eternal and cyclic, then we are not the singular, miraculous product of a one-time creation. We are a recurrence, a pattern that has likely formed countless times before and will form countless times again. This is not a demotion, but a liberation from the anxiety of a singular, fragile genesis. It suggests that life and consciousness are not fleeting accidents in a cold, empty universe, but may be inherent features of cosmic law, inevitable expressions of physics that repeat as long as the cycle turns. We are part of the universe's eternal return, a way for the cosmos to know itself again and again. Yet, this comes with a terrifying corollary. The laws of nature themselves may be transient. The delicate balance that allows atoms and stars and life to exist, the strength of gravity, the mass of the electron may not be fundamental constants but mere preferences, settings that were dialed at the last transition and may be dialed differently in the next. Our universe is habitable not because of a divine fine-tuner, but potentially because it is one of an infinite number of trials, an outcome that has been selected for by its own stability. We live in a universe that allows us to live in it. And so, the search for the signal leaves us with a transformed humility. We are not at the center of time. Our entire cosmic history, from the first flash of the Big Bang to the last dying star, may be but one heartbeat in an infinite life. The silence we now hear is not an emptiness, it is the sound of possibility. It is the space for our wonder. The question, what came before, has expanded from a scientific inquiry into a permanent part of the human spirit, a testament to our refusal to accept that any horizon is truly final. We may never receive the signal, but in listening for it, we have learned to hear the universe not just as a place of matter and energy, but as a story. And every story, especially the greatest one ever told, must have a beginning. The terrifying, beautiful possibility is that our beginning was also an end, and that in the grand, dark, cycling cosmos, every end contains the seed of a new beginning, forever. Chapter 8. The Unwritten Aeon. The investigation into the primordial does not conclude. It simply reaches the present moment, the leading edge of human knowledge. The story now transitions from one of discovery to one of potential. The tools are built, the theories are formulated, and the stage is set for the next great revelation. We stand at the precipice of a new aeon of understanding, looking into the darkness, waiting for the data that will either solidify our current cosmology or shatter it into a new, more magnificent form. This is the unwritten chapter, the future history of this mystery, waiting to be observed. The next great leap will be a synthesis of the cosmic and the quantum. For decades, the two pillars of modern physics, general relativity, which governs the very large, and quantum mechanics, which governs the very small, have remained stubbornly separate, describing their respective domains with unparalleled accuracy, but refusing to unite into a single, coherent theory of quantum gravity. The signal from before the Big Bang is the one phenomenon that exists at the violent intersection of both. To truly understand it, to even confirm its existence, requires a language that does not yet exist. The ongoing work on string theory, loop quantum gravity, and causal set theory are all attempts to write this first dictionary of the primordial. They are not just abstract mathematics, they are the necessary frameworks for interpreting what a telescope like LISA might hear, or what a CMB polarization map might reveal. The signal, if it is there, is written in the grammar of quantum gravity. We are now in the process of learning to read. This pursuit is transforming the scientific method itself. We are entering an era of extreme cosmology, where the key evidence is not a bright new star in a telescope, but a subtle, statistical ghost in exquisitely complex data. Verification will not come from a single eureka moment, but from a convergence of evidence across multiple, independent fields. A gravitational wave background detected by LISA that matches a specific non-inflationary pattern. A confirmed, statistically irrefutable anomaly in the CMB polarization that aligns with a prediction from Conformal Cyclic Cosmology. A particle discovered in a collider that can only be explained as a relic from a pre-epoch. The case will be built not on a single proof, but on a preponderance of clues, each from a different line of inquiry, all pointing toward the same unbelievable conclusion. This is a slower, more collaborative, and more profound form of discovery. And what if the silence persists? What if the next generation of tools, LISA, the Simon's array, the next generation colliders find nothing? What if the CMB remains random, the gravitational wave background is perfectly inflationary, and no relics are found? Then the silence itself becomes the data. A null result of this magnitude would be one of the most profound discoveries in the history of science. It would forcefully argue for the standard model and the absolute finality of the Big Bang singularity. It would erect a permanent barrier around the day, moment of genesis, declaring it fundamentally unknowable. It would be the ultimate negative result, teaching us that some mysteries are eternal, and that the human mind, for all its power, must eventually confront a wall beyond which it cannot see. This, too, would be a form of answer, a humbling and majestic closure. But the human spirit is not geared for closure. It is geared for the quest. The search for the signal from before the Big Bang is the ultimate expression of this insatiable curiosity. It is a project that may take centuries. It will certainly outlive every scientist currently working on it. It is a baton passed forward through generations, a long-term bet on the power of reason and observation. We are the ancestors in this story, the ones who first dared to formulate the question and build the initial instruments. The answer will belong to our descendants. They will be the ones to finally know if the universe is a one-time symphony or an eternal opera, if we are its only audience or merely its latest listeners. Our role is to ensure the question is never forgotten, that the tools are built, and that the search continues. For in that search, regardless of the ultimate answer, we fulfill our deepest purpose: to look into the void and listen, with patience and with hope, for an echo of our own beginning.